Okay, essay question 2. Hip hip hooray.
Good morning.
Good morning, America. I could probably cut out a whole bunch of the dumb stuff that's in the
Yeah,
other video.
that's probably true, but whatever.
Okay, so we're going to talk about osmosis, osmolarity, tonicity, and then we'll talk about RMP, which stands for resting membrane potential.
Ooh.
I will explain that one after I'm done the osmosis stuff.
No ways.
Surprise, surprise.
It's like it's second on the list.
Yep. Okay, so osmosis is defined as the movement of water across a membrane.
Okay.
So we have here
A beautifully straight line. Yeah, you need a new purple marker.
That's fine.
Good thing there's another purple marker right there. Ooh, cell membrane.
Yep. You remember what these are called?
Protein thingies.
Yes, but the ones that specifically move water.
Oh, it's the water protein thingies.
Aquaporin.
Right, yes, that was going to be my second guess.
Great. Okay. So osmosis is the movement of water across the membrane. It can move in, it can move out, do whatever it wants.
Sure.
So osmolarity. Actually, we'll start with what molarity is. Molarity. So if you'd ever taken a chemistry class, which I don't think you ever need to, molarity is moles over a liter of solution. In this case, we refer to that as like the water. A mole is 6.022 times 10 to the 23rd particles.
Okay, yeah.
So
Of something.
Doesn't matter. Say I have a 1 molarity solution of salt, sodium chloride, NaCl.
Okay.
That means I have 1 mole of salt particles in that 1 liter of solution.
Sure, and that would be the molarity there.
Yes.
Okay.
This one is actually, that's a really good example. I'm so smart.
Wow, look at you.
So 1 big M means molar, which moles per liter. NaCl, sodium chloride, table salt. Great. 1 molar solution, if I stick that in water, actually comes a 2 osmolar solution.
Okay.
So the reason is when salt goes into water, it dissolves. And these two things break apart.
Amazing.
So this, what osmolarity tells me is how many particles I have in the water. So because this just tells me how many moles of this thing I have. This tells me how many moles of particles I have. So
okay.
I have 1 mole of something that has 2 ions. But when I put that in water, that means I have 1 mole of the sodium and I have 1 mole of the chlorine.
Oh, yeah,
so it ends up being 2 osmoles because it's now moles of something in the water.
Oh, yeah, okay.
Make sense?
Yes, yeah, okay.
Great.
Cool.
So that's the difference between those two. Stay. And why that is really important, so your inside the cell has an approximate amount of 300 milliosmoles per liter. So around 300 millimoles of stuff.
Sure.
Inside the cell.
Okay.
And generally that's about the same outside the cell.
Okay, cool.
So, I'm going to erase these, and I'm going to draw boxes. This is box A, this is box. So, say this is your general cell. I'm going to draw 6 dots, and this is my 300 milliosmoles. this, we're going to say some other thing. I'm going to draw, say 4.
A different shaped domino.
Yes. When we talk about osmolarity, we have 3 different things that we have. We have hyper, iso, and hypo osmolar. So hyper osmolar means if I'm comparing A to B, this one has more particles than the one I'm comparing it to.
Okay.
So in this example, A is hyperosmolar to B because this has more particles in the same amount of water.
Right.
Let me draw the water in here.
Yeah, that's about a 2-dimensional liter.
Yeah. Great. Okay, then if I have the same amount of particles in both, it's iso-osmolar.
Okay.
Iso means same.
Yeah.
So
yeah,
hyper
okay.
means above. Before this had more than the other one. Iso means they have the same. Hypo.
Might I make a guess?
Yes.
Ah, you have more in the one you're comparing it to. If you're comparing A to B, B has more.
Yes. Yeah.
You're comparing, yeah, okay. So the one you're comparing it to has
more. So when we're talking about this, osmolarity only describes the comparison between 2 things.
Right.
Not what the water would do. Which
yeah.
That will make sense when I talk about tonicity. Really, really interesting and confusing thing. Water just moves because it does.
Awesome.
In the phys class, we talk about the more someone starts waving their hands, it means the less we actually understand about it. So when we talk about water moving something because concentrations of solutes are different, we're like, it just does. And then we wave our hands really big.
I see. That does make a lot of sense.
Yeah, we're just like, it moves.
It does. It does the thing.
Okay,
Nice.
so this makes sense.
It
So
does.
this example, A is hypoosmolar to B.
Mm-hmm.
But you could also say B is hyperosmolar to A.
Fantastic. Okay.
Great.
Reasonable.
So now we're going to do something super...
Follow-up question.
Yes.
Could you erase that little green bit? That's like, okay, that bugs the freak out of me. Okay. Anyway.
Big box.
Ooh.
Filled with some amount of water. Doesn't have to be a 2-dimensional liter.
It's at least like 2-dimensional liters.
This is a cell.
I see. That's, yeah, okay. It's probably not a liter then.
It's a really, really big cell. This is an ostrich egg.
Oh yeah, okay.
Biggest single cell. So in the current condition, what is the osmolarity of the cell compared to the outside fluid?
Hyper.
Yeah, hyperosmolar.
Yeah. Okay.
This has more than this.
Okay.
So the interesting thing that happens is water will move from an area of low osmolarity to high osmolarity. So move to the place that has more particles.
Beautiful.
So I'll use blue.
Because water.
Because we're not really sure why.
It just does.
It just does. The current way that they explain it is, this is assuming that these particles can't move through that membrane. So what they assume happens is like the particle bounces off the aquaporin and then creates a pressure difference and pulls the water in. Which I'm like, makes sense, but I'm like, huh? So this then starts describing what we call tonicity. I'm going to write the word. Tonicity. And so same with osmolarity, we have similar things. You can have something that's hypertonic.
Isotonic and hypotonic.
Correct. Hypotonic. And so those describe the movement of the water.
Okay.
So in the current situation, actually, even if I move like, so 6 dots means 300. Each dot is approximately 50. So this is only like 200 milliosmoles. Water's still going to move in because this has more particles of stuff.
Sure.
So started out and is currently high per osmolar. Once water moves in, this will fill up. So if water moves into this, it's called hypertonic.
Okay.
So the cell is hypertonic to the solution.
Yeah.
So osmolarity is when I'm comparing two different things that aren't interacting with each other.
Okay.
Tonicity is once I stick something into the other and then water starts moving.
Okay, so tonicity moves in the direction that the osmolarity of the same suffix.
Not always.
Not always?
Not always.
Oh,
no,
because it just do.
No, I'll actually explain this one.
Oh,
this
okay.
one makes sense.
Okay.
So if I have something like, say, sodium chloride, a really good example is IV bags in hospitals.
Sure.
So there are 2 types of IV bags that are isoosmolar, so same number of particles as the general concentration within our cells. And so those two are 0.9% NaCl. This is also called a saline solution because salt.
Okay.
And then a 5% dextrose. And dextrose is just sugar.
Right.
5% dextrose solution. So both of those are approximately, the 300 milliosmoles that the inside of our cell is. But the interesting thing, so say these purple dots, those ones, actually, I'm going to make them something else. I'm going to make them stars.
Ooh.
So each of those represents some kind of like salt particle.
Okay.
So this has, 300 and that has 300.
Yes.
Because they can't cross the membrane easily, I have the same amount of particles inside and out. Isoosmolar.
Right. Yes.
And because I have the same inside and out, water's not going to move.
So it's isotonic as well.
Also isotonic. Yes.
Okay.
So then, what happens if I make it to where this stuff can actually move across the membrane?
Well, then you're going to have an imbalance, right? So you'll have to
Yes.
add something to, the outside.
Mm-hmm. Good. So now I'm going to start drawing little holes. And this will mean that this membrane is permeable to these stars, which I'm now going to define as dextrose.
Okay.
So remember when we talked about the potassium goes from high to low?
I do.
Wants to reach equilibrium. That will happen with these dextrose. So at the beginning, it starts like this, but then what happens is then I get some inside the cell.
Sure.
So now water is going to move where?
Well, it's osmolar.
Was, yes, at the beginning.
And it's not now.
No.
Because there's a different number of
Stuff.
dots.
Yes. More stuff.
Okay, so yeah, the water's going to go inside, even though there's the same number of stars.
Inside and out. But now I have more particles inside. And water's going to try to, the way it's described is going to try to reduce the concentration to be equal concentrations inside and out.
Okay.
So now, even though it started out as iso-osmolar, because water is moving in, the cell becomes hypertonic, and the solution is hypotonic.
Okay, yeah. Right.
Okay. So now, the super interesting thing is what happens if I combine these two?
And you put them both on the outside of the cell?
Mm-hmm.
Well, then it's just gonna be hypertonic in both ways. Surely.
You'd think so, wouldn't you?
I sure would. Okay. Doc.
Okay, these ones are. That's our salt. Cannot get into the cell, right? Because I said it doesn't get through the membrane.
Right.
Then we'll put in. That's our sugar molecules. So,
Okay.
starting.
And there's no sugar molecules inside the cell currently.
No.
Okay.
Starting
Following.
initially, this is hypoosmolar because this has less particles than the outside does.
Yep.
Great. However, time goes on because we said the cell membrane can allow the sugar to move in.
Yep.
So now, if we count the number of particles, this has 9 on the outside and that has 9 on the outside. In terms of tonicity, water didn't move because the concentrations are balanced.
Yeah, right.
So even though originally the cell was hypoosmolar to the outside, it's considered an isotonic solution because the water didn't move at all. Make sense?
Yeah.
So the way that our textbook describes it is tonicity is kind of effective osmolarity. So osmolarity describes the state of something, tonicity describes the movement of the water and what actually happens.
Reasonable. Cool.
Okay, that's osmosis and all that stuff.
Okay.
Now we're going
Follow-up question.
Yes.
There's a little speck that you left behind. Okay.
Great. Okay. Now we're going to talk about resting membrane potential.
A beautiful line. Oh, a cell membrane.
Thank you. Okay, so resting membrane potential describes that voltage difference across the membrane. So remember when I was talking about the separation of charges?
Yes, I do.
Okay, so your average neuron has, I'm going to draw a fun little graph here. We put that at 0, and this is going to be negative 70, and this is in millivolts, and this is time. So your regular membrane is sitting at about negative 70 millivolts. So basically what that means is, so we have high concentration of potassium inside, really small outside, and then high sodium outside and low sodium inside. And so the way that the cell sets up this thing is through what's called the sodium potassium ATPase pump.
That's complicated.
Yeah. So basically what it does is it will pull out 3 sodium and will pull in 2 potassium, and it will use ATP.
Oh yes, I remember this. Okay.
So it uses energy to start setting up this gradient. High sodium, low sodium, and then high potassium and low potassium outside.
Right.
This sodium potassium ATPase pump is literally the reason why we are alive.
Okay.
So our cells have tons and tons and tons of those. So sodium is generally impermeable to the membrane. Doesn't really cross it. Potassium, on the other hand, does. We have these proteins called potassium leak channels, where potassium can slowly leak out following down the concentration gradient.
Right.
And so we talk about these things having charge. This is a positive charge, but there's always also negative charges to counteract those, because you can't have something that's a positive and you have no opposing negative. Opposition in all things.
Of course.
Right? So we also have a bunch of negative charges in here. So, for example, if I have this box, and we're going to say that it is only permeable to potassium. So I have a bunch of potassium in here. We're going to draw 5. But when I add those, say I also add chlorine, because it's the thing that I added is potassium chloride, because I can't have positive negative stuff. So chloride, and then I have the same amount inside. So our chlorine is that negative charge, potassium is a positive charge. If my membrane is only permeable to potassium, wouldn't you say that the potassium, some of it is going to flow out here because it wants to reach equilibrium?
Yeah, I would say so. Okay. I think so.
So, one potassium is going to move out, maybe another one is going to move out.
Sure.
What this does to the charges is actually super important. So originally, I'm going to erase those ones that moved. So originally, they were both net neutral. Yes. This one has the same number of positive charges and negative charges.
Yeah, okay.
And this one didn't have any charge at all, so it's just neutral as well.
Right.
Now, if I count up my charges, this has 2 positive more than before, and this now has, a net of 2 negative. So you see how I'm now separating charges?
I do.
So what this does,
okay.
This sets up some kind of potential for something to move the potassium back over, because, opposites attract.
Yeah, okay.
So this is what these leak channels do, is as positive charges leave the cell, it ends up making the cell negative on the inside and positively charged on the outside.
Okay.
Make sense?
It does.
Great. And so this sets up that approximately negative 70 millivolts that you will have for an average neuron.
Yeah.
Okay. So some things that can change what this is set to. If I have, say I have more potassium outside the cell, the potassium inside the cell isn't going to want to leave as much because there isn't as high of a difference.
Yeah, okay.
So if I have, like in this box, I had, 5 on this side, but what if I had, so actually a better example would be so here's my box, say I've got 20 in here and then 5 here, it's going to want to move here till I reach some kind of equilibrium.
Okay.
But what if I have, 20 here and 10 there? It's not going to want to move as much to make it equal.
Oh, yeah, okay.
So if I increase the amount of potassium on the outside, wouldn't you say that I now have less positives outside?
Say that again.
If I increase outside potassium with chlorine, so it's still a net neutral addition, less potassium is going to leave the cell.
Yeah, okay.
Which means I have less separation of charges.
Yeah.
Because I have less potassium leaving behind the negative stuff.
Yeah, okay.
This ends up making this go higher. So the more separation, the lower that is. But if I have less separation, it could actually potentially sit here, say, maybe negative 65 millivolts.
Right.
So if I increase potassium, my resting membrane potential, which is the separation of charges, goes up.
Okay.
And then, if I have even less, so say instead of increasing it to 10, I now have 20 and I reduce it to 1. Even more is it's going to want to go even more.
Right.
So if I have, even more, then I have an even higher separation of charges, which will actually end up dropping this. Make it even more negative.
Oh, wacky, okay.
Does that make sense though?
Yeah, okay. Interesting. Huh.
Okay. So that is the stuff that can change our resting membrane potential. Now we're going to talk about Nernst and driving force.
Okay.
So I wish I didn't keep erasing the ECF and ICF. Oh, I'm making way better time. Only at 25 minutes and I'm almost done. This is great. Okay, so we have, I'm just going to draw some kind of cell. Big potassium, little potassium, little sodium, big sodium. That's an A. Okay, so we have this thing called the Nernst potential. So this is, it's named after a dude, the last name of Nernst. So the equation is something really weird. Those boxes means the concentration inside or outside.
Right.
So high concentration, low concentration.
Okay.
Log is log.
Right.
Z refers to the charge of the ion.
Excellent.
So if it's something like sodium, that would be a +1.
Go on.
If it's something like calcium, this would end up being a +2.
Following.
If it's something like chlorine, it would be a -1.
Excellent.
Okay.
Yes, continue.
So this describes that if this were the only ion there, it would tell me what this resting membrane potential would be.
Perfect. Okay.
So for potassium, the E of K plus is approximately -94 millivolts.
Excellent.
For sodium, it's approximately like it's like 100 something. Yeah, I'm just gonna say 100. It's around 100.
I see.
So this describes, so with that drawing that I had where I had the separation of charges, if sodium moves into the cell, that makes the outside become more negative because I'm removing positives, and then the inside becomes more positive.
Oh, yeah.
So it ends up being something more like this.
Okay.
So that's what would happen if sodium were to do that. And when we look at this number, it's always inside opposed to outside.
Right.
So -70 as opposed to, whatever that is.
Okay.
So this is our Nernst equation. This describes, what this would do if it was just on its own. Driving force is another important thing. We're going to move it here. Hello, Kirby. Driving force. So we're going to do D is equal to Vm, which is called voltage of the membrane, minus E, which is our Nernst potential.
Excellent.
So for something like potassium, we take this number, so -70, and then we subtract this, which ends up being into a +94. So this ends up being about, +24. So driving force, that number is always placed inside the cell. So I'm going to put a +24 for potassium. Do positive things like to be near each other?
No.
No. So this means potassium wants to leave the cell by 24 some amount of arbitrary units.
Right.
Now if we look at sodium, we have our -70, which is what the membrane is sitting at,
Right.
minus that 100,
Ah.
which ends up being a -170. And
Yeah.
this number is always placed inside the cell.
Okay.
So now we have high amount here, and this is a negative. This wants to go in. So this number describes how strongly it wants to move into the cell.
Which is a lot.
This is like super duper strong. For calcium, it's like 200 something.
Oh gosh.
So this describes how strongly something wants to go in.
Cool. Interesting.
And then eventually those will change this membrane potential when we get, once I talk about stuff called action potentials, which is how your neurons fire.
Okay. Cool. Yeah, I will remember all of those equations.
You don't have to. That's okay.
No, I yeah, it's already in there, you know?
Right.
I'll never lose it, and yeah.
That's it.
Very cool.
Any other questions?
How does this all relate to Kirby?
So Kirby is a living organism,
Okay.
and the way that his eyes work is based off of these different potentials.
His eyes?
His eyes, yes. So when light hits the neurons in the back of your eyes, those cause changes within specific chemicals, which then leads to a pathway of sodium rushing into the cell, making it more positive, which then sends signal down the neuron to your brain, which then your brain processes those stuff and it says, oh, I'm seeing this. And then sends signals to other stuff, other effectors, which then will make Kirby either, run around, jump on something, kill Dedede, or
wow.
Yeah.
Polio. That's fantastic.
Any other questions?
No.
Great.
No.